The first thing we'll try to do is to notice something which you may have noticed already. We have three equations, but we have four unknowns. We have W, U, and V, and we have H, which is also a function of latitude, longitude, and time. So the first thing we'll do is then jump to integrating this in the vertical. We have a shallow water system, and we will just take the continuity equation with its mass source. We will set the mass source to 0 and also the background state to 0 for simplicity, and get into our tropical systems away from the tide that Laplace was trying to do. Then you have the vertical term and the horizontal terms. You know, as soon as we say we integrate in the vertical, we're going to use the boundary conditions to simplify the situation and produce a additional equation for W, so that we come up with now 4 equations for 4 unknowns. Okay, so the initial Z independence assumption implies that U and V are independent of Z. So Laplace had imagined a rigid body system, so the fluid columns are just going around without varying in the direction of the rotation. For some of you, that may remind you of Taylor columns, right? The Taylor-Proudman theorem and so on. So if you have a quantity alpha, when you average it in the vertical, you're going from the bottom, HB, to the top, H, and integrate in Z, which we do for W. So at Z equal to H at the top, it is basically the variation of the surface itself. That's the W, right? At the bottom, W is equal to 0. Very straightforward, right? So this immediately gives us another equation when we integrate, but this also implies that we are going to make it horizontally non-divergent. Let me make sure. Yeah, not horizontal. It's independent of Z. So du dt minus fv, this is the set of equation we saw with now 3 unknowns, u bar, v bar, and h, because we have figured out w already as in terms of h as dh dt. Then we will linearize the system, and some of you already are experts, and we know that when you linearize, you're going to look for wave modes and so on. So the system can be linearized by assuming U to be the background state plus the perturbation, and V to be just the perturbation, because in the meridional direction we don't have a background state, background flow. And H is the H bar plus HS, the meridional slope, plus the perturbation to the free surface. Obviously, when you do these kind of splits, you always have the assumptions of small perturbations. So U prime and V prime are much less than the mean flow, and H prime, the perturbation, is smaller than the perturbation, the variability of the free surface. So you can imagine that as if like you have the Earth rotating. There is a dynamic adjustment which creates the sea surface height, and then you're perturbing on top of that. So you have a sea surface height already as a function of longitude, latitude, and time, and you are perturbing on top to a small amount. So it's much less than h. Okay. Then we can stipulate that u prime and u prime times u are much greater than the perturbation terms squared, like u prime, and v prime terms. And we assume that the mean depth h bar is much greater than the meridional slope, which is giving us the background geostrophic flow in the zonal direction. Okay, for linearization we need that. Then we write the equations in the perturbation form. So du prime dt plus u bar du prime dx, we have gotten rid of the appropriate terms, plus v prime du bar dy. We will see in a minute that this is the Doppler shift term, and this is the non-Doppler shift term. So this is an intrinsic balance problem, and this is the shift because of the background state we already talked about in the wave kinematics, right? This is the FV prime term in the x direction, and the GDH prime dx term, which is the surface perturbation or the vertical term. dV prime dt in the meridional direction plus the Doppler term plus there is no non-Doppler term in the sense of this advection here. It's just Fu prime and the vertical term. And our continuity equation now can be written in terms of dH prime dt plus U bar dH prime dx minus the beta term, right? Because you have V prime and U bar, you're going to have the contribution of terms to perturbation of the free surface, plus the horizontal divergence term of the perturbed field. Okay, so we have assumed here again H bar is much greater than Hs, and there is no source or sink of mass. So obviously you have to jump back to the scaling discussion now. Every time you do this kind of split, you have to start thinking about scaling and see which terms dominate and what the non-dimensional numbers may be, etc. So it's interesting to note that 5.8c here has the H bar term. So if H bar becomes big, depth of the water column, you can think of it as equivalent depth, becomes larger, then this term can dominate and these terms can become smaller comparatively, which means you become non-divergent or barotropic. Okay, so correspondingly, this term has to become smaller and smaller or go to 0 if H bar times this term has to be equal to 0. So larger, deeper the water column or the atmosphere column, H bar, more barotropic the fluid is going to be, and non-divergent. So assuming a motionless base state, as H becomes larger, the system must become increasingly non-divergent for balancing the other equations, just for consistency. Simply in terms of x and y momentum equations and the continuity equation. If simply H is sufficiently large, the last term dominates. But to satisfy this, as we said, the horizontal divergence has to go to 0, vanishingly small. And if the fluid is very shallow, then increasingly divergent motions become possible. Okay, so no non-dimensionalization is done yet. So the Doppler and non-Doppler effect, basically Doppler effects are those that refer merely to translation of a characteristic by the basic state, which is what we had done before in terms of the modulation of the wave mode frequency wave number by the background state. And the non-Doppler effects result from intrinsic changes in fundamental balances needed to support the basic state. So you can think of this as meridional advection of the mean state, meridional advection of the gradient of the mean state, meridional gradient of the zonal geostrophic current by the meridional perturbation velocity. Okay, so we'll leave these for this podcast and come back to equatorial waves quickly. So as soon as you do now linearization and some scaling, you know you're going to jump to wave solutions, because that's the main purpose of doing linearization anyways.